Okay, so science of statistics is the most useful servant, but only of great value of those who understand its proper use. So this is a statement given by a famous statistician, King. The occurrence of cancer is known to be related to the number of factors, including age, sex, time, and ethnicity, as well as exposure of environmental agents such as ionizing radiation. Understanding the role of exposure is occurrence of cancer in the presence of modifying effect is a difficult problem. So contributing to the difficulty are the stochastic nature of cancer occurrence, both background and exposure related, and the fact that radiogenic cancers are indistinguishable from non-radiogenic cancer. So there are two essential components of risk assessments are a measure of exposure and number two, a measure of disease occurrence. So some individual exposed to environmental some individual exposed to environmental carcinogens, that is ionizing radiation, develop cancer, and some do not. Okay, so all are not related to develop the cancer. The same is true of unexposed individuals. Thus, the cancer is not a necessary consequence of exposure, and exposure is not necessary for cancer. However, the greater incidence of cancer in individuals exposed to no carcinogens indicates that the probability or risk of developing cancer is increased by exposure. So compared to unexposed individual, the related risk of exposed individuals are manifest by increased cancer rates in the latter group. So risk and rates are the basic measures used to compare disease occurrence in exposed and unexposed individuals. In the next slide, we describe the rates and the risk and their relationship to one another, and as a prelude to the section on modeling and model fitting. A common measure of disease occurrence used in cancer epidemiology is the incidence rate. Incidence refers to new cases of disease occurring among previously unaffected individuals. The population incidence rates is the number of new cases of the disease occurrence in the population in a specified time interval divided by the sum of observations time in that interval on all individuals who were disease free at the beginning of the time interval. In general, an incidence rate is time dependent and dependent on the both the starting point and the length of the interval. So with the data from studies in which subjects are followed over time, incidence rates can be estimated by partitioning the following period into intervals of length that denoted by Lj having midpoint, that is Tj, for j equals to 1 to j, and estimating the rate of each interval. So measuring exposure of to radiation is challenging problem and discriminatory issues. So evaluating the association between exposure and disease occurrence is added by the use of statistical models. And the type of models commonly used in radiation epidemiology are described. So here let Nj denote the number of individuals who are disease free and still under observations at time Tj, and Dj the number of new diagnoses during the jth interval. An estimate of the incident rate at time Tj is obtained by dividing Dj by the product of Nj and Lj. So incident rate given by the equation lambda cap Tj that equals to Dj divided by Nj Lj. So in the denominator is an approximation of the sum of observations time on the Nj population members in the jth interval, and in practice is usually replaced by the actual observations time, which accounts for the fact that the Dj diagnosis of disease did not occur exactly at time Tj. Then risk is defined as the probability that an individual develops a specified disease over a specified interval of time, given that the individual is alive and the disease free at the start of the time period, as with the incidence rate, risk is the time dependent and dependent on the both of the starting point and the length of the interval. In a longitudinal follow-up study as described above, the proportion of the new occurrence Dj among Nj disease-free individuals still under observations at time Tj. So this is the probability that P cap Tj equals to Dj over Nj, this is the ratio, is an estimate of the risk of probability of disease occurrence in the jth time intervals. So incidence rate and risk are relative by the general formula rate equals to risk equals to rate into time. For the longitudinal follow-up study estimates define above the relationship in manifest by the equation. This is the probability of this. So this is the multiplication of incident rate and time. The description of rates and risk in terms of estimate from the longitudinal follow-up study is informative and clearly indicates that the relevance of these numerical equations to the study of disease. However, the development of general theory of risk and risk estimation require definitions of rates and risk that are not tied to particular types of studies or method of estimation. So the probability model provides the mathematical framework for studying incidence rates and risk, and also used in defining statistical methods of estimation depending on the types of study and the data available. So here we have defined here the models of studying the relationship between disease and exposure are usually formulated in the term of instantaneous incident rate, that is hazard rate, or which is theoretical counterpart of the incidence rate estimate defined below. Okay. So two functions derived from Ft and Ft used define the instantaneous incidence rate. One of the survivor function, which is probability of being disease free throughout the interval T0 to T and is equals to 1 minus Ft. Okay, so where Ft is the time of that is the probability distribution function of the time of disease occurrence. Okay, so one is the total probability, then 1 minus Ft. Okay. Then the second is the probability density function, which is derivatives of Ft, which is with respect to T. So that is Ft equals to derivative of Ft with respect to T, and measures the rate of increase in Ft. Okay. So the instantaneous incidence rate, also known as the hazard function, or is the ratio. It is given in the equation lambda t equals to Ft over 1 minus Ft, and Ft is the probability function and Ft is the probability density function. Integrating the instantaneous incident rate is the cumulative incidence rate. Okay, so this equation gives the cumulative incidence rate, that is delta t equals to integration of 0 to t lambda t, so lambda u du. Thus, the cumulative incidence rate and distribution function satisfy the relation Ft equals to 1 minus exponential of e to the power minus delta t, from which it follows that the instantaneous incidence rate completely determines the first occurrence distribution ft, then the risk of the first disease occurrence in the interval t to t plus h gives no previous occurrence is the conditional, and the conditional probability of given as this probability of t to t plus h, that is ft plus h minus ft over 1 minus ft. So this equation gives the conditional probability when h is not too large, so that the difference quantity ft plus t minus ft divided by h, this is a function approximate ft, small ft, that is derivatives of probability density function. So thus among individuals who are disease free time at time t, the risk of disease in the interval t to t plus h is approximately lambda th. This approximation is the theoretical counterpart of the relationship between risk and rate described in the discussion of risk. In the remainder of this incidence rate means instantaneous incident rate unless explicitly noted otherwise. So then here we are discussing about the incidence rate and excess risk. It is clear that the incidence rate plays an important role in the stochastic modeling of disease occurrence. Consequently, models for studying the dependence of disease occurrence on exposure are generally formulated in terms of incidence rate. In the following is the assumed that individuals have been stratified on the basis of age, sex, calendar time, and possibility of other factors related to disease occurrence, and that incidence rate are stratum specific. So in the simple case of two exposure categories, exposed and unexposed, let lambda t, lambda et and lambda u2 denotes the incident rates of exposed and unexposed group respectively. If disease occurrence is unrelated to exposure, one expects that lambda et equals to lambda et equals to lambda ut, whereas lack of equality between these two incidence rate indicates an association between disease occurrence and exposure. So a common measure of discrepancies between incidence rate is the difference, that is excess absolute risk equals to lambda et minus lambda ut. So technically a difference in rate rearranging terms result in, that is lambda et equals to lambda ut minus plus excess absolute risk t. Okay, so it is nothing but it is the rearranging of the terms or equation. So we can find the incident rate of exposed and unexposed group by rearranging this equation. Okay. The second common measure of discrepancies is the relative risk. It is defined as the ratio of two risks, that is lambda et, and so lambda et denote for incident rate for exposed and unexposed. Okay, so this is the ratio of exposed and unexposed incident rates. Okay, so again we are rearranging terms, that is for the second common measures of discrepancy for relative risk, so that the relative risk describes the multiplicative incidence in incidence rate associated with exposure. When the relative risk is constant, that is say R, the effect of exposure is to after incidence rate by the factor R. If the exposure incidence increases risk, then R greater than 1. If exposure decrease the risk, then R less than 1. And R equals to 1, that is correspond to the case of no association, then axis relative risk. So the axis relative risk equals to relative risk minus 1. Then the axis relative risk of the exposed and unexposed incident rate are related by the equation, that is incidence rate of exposed equals to incident rate of unexposed, and this is 1 plus exposed relative risk. Okay. So then risk models. So we can develop here the risk model, direct estimate or other models. So for direct estimates, in the previous section defined the fundamental quantities used in risk estimation, that is risk, rate, exposure, relative risk and ERR. For the most carcinogens, exposure is not a simple dichotomy, that is unexposed and exposed, bivariate, but occurs on the continuum, that is the exposure of dose, that is D. At D can be vary from no exposure, that is D equals to 0, upward. In such cases, the relationship between risk or the axis absolute risk or absolute relative risk and dose is of the fundamental importance. For all carcinogens, is it generally agreed that sufficiently large doses increases the risk of cancer. So by the definition, there is no increase in the risk in the absence of the exposure, that is D equals to 0. When D equals to 0 or both axis absolute risk and axis relative risk are 0. Thus, for many carcinogens, the only open or unresolved issue is the dependence of risk on small or low doses. So low dose range are often the most relevant in terms of numbers of exposed individuals. They are also the most difficult ranges for which to obtain unequivocal evidence of increased risk. So these difficulties results from the fact that small increases in the risk associated with low level of exposure and difficult to detect using statistical models in the presence of background risk. So direct estimate of the axis risk for the ith time period in the differences between two proportions dje divided by nje minus dju over nje. Okay. So even in the favorable situation in which the baseline risk is relative well this. Okay. So for example, using the usual criterion for statistical testing in order to detect the probability 0.8 and 5% increase in the risk when the baseline risk is 0.0, when the number of individuals at risk in the exposed group would have to be approximately NG equals to 30,000. Okay. So risk model Continue, that is estimation by mathematical modeling. There are lots of mathematical modeling available. So Amrita's 1985 developed some models. The corresponding hazard function is of the form delta t equals to at raised to the power k minus t, where t denotes the time and a is the constant. So using this constant, some empirical models, empirical based is also developed. The following symbols are used to describe the variables that enter into the risk model based on the Japanese A bomb superior data, survivor data. So A, attaining age of individuals, E, age at exposure of radiation, D, dose of radiation received, S, code for sex, T, study population specific factor. So using these, we have to develop some models by multiplication and addition. So these are the models we can develop and for our study purpose. Okay. So radiological considerations is that the low dose and low LET, that linear energy transfer radiation, the risk of disease for an individual exposed to dose D depends on the linear and quadratic function of D. That is, risk depend on the dose D through a function of the form. So these are the forms of models. In general, the model applicable to the broader dose range and used extensively in the radiation research. That model given by Efri. So variable selection, variable that can selection for the models, modify the dose response relationship, use so model for example, the committee preferred model for solid cancer uses this. So model parameter estimation model describe the mathematical form of the risk model, but the parameters in the model must be estimated from the data. For example, a linear dose model presupposes that the risk increases linearly with dose, but the slope of the line which measures the increase in risk for the unit increase in the dose must be estimated from the data, just like linear regression equation, y equals to a plus bx, and some other method also available in the literature to estimate the models. The parameters are estimated by those values in the parameter, that is space, the set of all allowable parameters values that maximize the likelihood for the given data values. So there are several approaches for the numerical calculation of the likelihood analysis. Estimation based on group data using a Poisson form of the likelihood that developed by Carlton and Hills 1993 has been used for analysis of atomic bomb series survives and other major epidemiological studies for radiation of health risk. Thank you.